The Kintaro-candy repeating decimal. A very mysterious and interesting decimal. A Kintaro-candy is a traditional Japanese candy shaped like a long cylinder. Usually they are sold after being cut about 1 cm long, as shown in the animation. The first characteristic of this candy is that the same figure appears in the cut surface no matter where we cut it. In a Japanese folk tale, Kintaro was a Superman-like child, carried a broad axe, defeated a wild bear, and made the bear a follower. Japanese parents sometimes displayed a doll of Kintaro, in hope of a child being brought up well. Kintaro is also the most popular motif of the Kintaro candy, so that Kintaro candy becomes a generic name of this kind of candy. The candy has many figures other than Kintaro animals, anime characters, fruits, and so on as shown in photographs. I call certain repeating decimals Kintaro-candy decimals. Because this Kintaro-candy decimal has a very interesting nature, before I explain what a Kintaro-candy decimal is, I would like to show this nature. As you know, a repeating, or recurring, decimal is the decimal representation of a number whose digits repeat at regular intervals. For example, in the decimal 0.623362336233, 6233 is the repeating unit, it repeats endlessly. This is one example of a repeating decimal. A Kintaro-candy decimal is a type of repeating decimal with a very exciting feature. Now, let's make a Kintaro-candy decimal. 6 numbers form a circle in the figure at left. To make a Kintaro-candy decimal, pick any one of these 6 numbers as the first number of the decimal. Then move clockwise to pick up more numbers for the decimal. After you have picked all 6 numbers, place 0 point at the front of the sequence. For example, if I pick 1 as the first digit, the following numbers are picked up in turn clockwise: 4, 2, 8, 5, 7. Then add 0 point before the start of that sequence. The decimal I made is 0.142857. To do an addition and subtraction, make one more decimal. Again, pick up any of the 6 numbers, then pick up the following numbers in clockwise order and place 0 point at the front. As I explain later, depending on the combination of decimals selected, we do not always see interesting results from both subtraction and addition. In this example, I pick up 2 as the first number of the second sequence. Then the following numbers are 8, 5, 7, 1, and 4. The second decimal is 0.285714. Then I add the 2 decimals I have made. 0.1428571 plus 0.2857142 equal 0.428571. The answer is surprising, because it is the same number sequence with a different starting point. Next, we try subtraction. 0.285714 minus 0.142857 equal 0.142857. The answer we get by subtraction of these repeating decimals also becomes the same number sequence with a different starting point. When a Kintaro-candy decimal is added to or subtracted from another one, the answer always becomes a Kintaro-candy decimal, or, as mentioned in the next paragraph, 0 or 1. This is the specific feature of a Kintaro-candy decimal. Depending on the combination of selected sequences, the answer may become 0 or 1. When you select the same number as the first one to make a second decimal, the result of subtraction becomes 0, in this case, please perform only addition. And when you select the number that is diagonal from the first one you chose, the result of addition becomes 0.999999, that is, 1. For example, if you select 5 to start the first decimal, and then choose 4, diagonal from 5, to start the second decimal, the resulting decimals are 0.571428 and 0.428571. Adding these two decimals produces a sum of 0.999999. In this case, please perform only subtraction. The most striking feature of Kintaro-candy decimals is that when they are added to or subtracted from each other, the answers are always recurring decimals with the identical number sequence. This Kintaro-candy decimals above are all fractions of 7. 1/7 equals 0.142857. 2/7 equals 0.285714. 3/7 equals 0.428571. I omit the subsequent parts in a voice. As shown above, the answer becomes the identical number sequence except the starting number, when integers are divided by 7. Just imagine that when a line segment from 0 to 1 is divided by 7, all sections of the segment show the identical number sequence, and imagine that when the decimals are arranged in a circle, all sections are the same. These circles look like a section of Kintaro-candy, therefore, I designated this type of decimal as a Kintaro-candy decimal. I think you can understand the reason why adding or subtracting Kintaro-candy decimals produces answers that recur to the same sequence of numbers, never any other decimals, or 1 or 0, depending on the combination of decimals. When we add or subtract some number of sevenths and slash from some number of sevenths, the answer always becomes some number of sevenths. Note, 1 is 7/7, and 0 is 0/7. Why will the answer become the same progression when numbers are divided by 7? To find the reason, let's divide 1 by 7. After 6 division steps, the remainder becomes 1, so the calculation recurs to the start. Please pay attention to the remainder at each level. The remainders are from 1 to 6, and each number appears only once. If you want to divide 2 by 7, you do not need to start a calculation anew, you can copy the answer of this calculation from the place of remainder 2, at the third level, as 0.2857. Because the remainders are 1 from 6 and each appears only once, when all integers, except the multiple of 7, are divided by 7, you just copy the answer here from the corresponding number to get the answers. Therefore, the answers when all integers, except multiples of 7, are divided by 7 become decimals which show the identical number sequence. Other fractions besides the fractions of 7 can become Kintaro-candy decimals. Here are some examples. The next Kintaro-candy decimals are the fractions of 17. 1/17 equals 0.0588235294117647. Then come the fractions of 19. 1/19 equals 0.052631578947368421. I omit the subsequent parts in a voice. Finally, I would like to introduce the most wonderful feature of Kintaro-candy decimals. The Kintaro-candy decimal of the fractions of 17 is 0.0588235294117647. The repeating unit of this decimal is divided into two parts, a former half, 0.588352, and a latter half, 94117647. Add the first numbers of each half, namely, add 0, the first number of the former half, and 9, the first number of the latter half, the answer is 9. And then, in like manner, add the second numbers of each half, add the third numbers of each half, and so on. All answers of the addition are 9. This astonishing feature is common among Kintaro-candy decimals. If the number sequence of any Kintaro-candy decimal is divided into former and latter halves, the sum of numbers of the same order in the former and latter halves is always 9. Because the latter half number sequence is easily derived from the former half sequence, the rest of the answers are already obtained before the division process finishes. What a mysterious feature, don't you think?